Hey, welcome to Coffee Compiler Club. I'm here to talk about compilers and type systems and whether or not you can do const references to C++ assignments or register allocation or anything and everything. Um, as a forewarning, the next 2 weeks I am off at Burning Man. You can see my Burning Man haircut. It's good to go. And then I'll be back 2 weeks after, the week after that. So probably skipping the 22nd, 29th, on again September 5th. Okay, that's the end of the opening spiel. Oh, everyone's been recorded here. We all show up on YouTube in a couple hours. Um, and Ryan, you were trying to tell us about something to do with C++ default move.
Oh, well, I was contrasting with mine. Why don't we let register allocation guy go first? Because mine might be a little bit long.
No,
No,
I'm still writing my question out.
yes, he said he
Oh,
was not ready yet.
okay. All right. Well, okay. So I've been working on my language runtime front end and stuff. Um, and so I was kind of trying to implement like default moves and like basically just the defaulted operations. And I was starting to think about this a little bit. And I was like, in C++, which is kind of what my language is pretty similar to, right? You most of the conventions is when you do an assignment operator overload, usually you take like the parameter of the other object by a reference. And so you'll take it by const reference or temp reference, like our value reference, right? Um, but what I was realizing is kind of like whether or not that is the right way to take an assignment by default. And I was thinking, what if instead of taking these parameters by reference, we take them by value? Because if you take them by value, then you just need to call the constructor. Like if you pass a temporary and the assignment operator takes a value, it'll still call the like move constructor, but then it'll pass that like move constructor value into the assignment operator by value. And then what you can do is you can have the assignment operator just be like a swap operation. And so you can like default implement the assignment operator for any type that has a move constructor just by doing a swap internally and taking the parameter by value.
Uh, yeah, I'm more or less morally opposed to what C++ has done with copy and move operators. Um, Overloading them to make user-defined semantics in my head is sort of asking for various kinds of trouble. And if you have to say something about them, like if the defaults aren't sane all the time, then oh my God, it's a nightmare of you endlessly have to write something.
Well, yeah, I was thinking because the way C++ works, you have to define both the copy assignment, the copy constructor, the move
Right.
assignment, and the move constructor. And I was thinking if I default the assignment operator to take a parameter by value, you only have to do the constructors, and then that assignment should work in like most situations, right? If you take the parameter by value and then swap, it'll always work basically. So I was thinking that's one thing. And so I was also thinking of a couple like scenarios here, right? So let's say I have like a copy on write object. Let's call it X, and X has like X dot B. And if I say X dot B equals X, right? With the current C++ way of doing things, if I'm, in my copy on write, I'm like X dot edit dot B dot edit equals X. That doesn't work because you're reading and writing an object at the same time, so you have to like copy X,
Why?
y equals X.
I'm sorry. Why does that not work? Like the obvious
um
thing is I have a linked list pop and, you know,
okay, so
list head equals list head dot next.
right, so this is basically like sort of a race condition on a copy on write in a way. So if
Yeah.
I'm in dot edit, I can't be dot read on the same object at from the same handle. So like copy on write objects, the way that they work
But isn't
in
the read go first? It's not at the same time. The read goes first.
no, it happens at the same time actually. So like it returns a reference, right? So if I call dot edit, that returns a reference. And if I'm calling dot edit and dot read on the same object, that's kind of like a race condition because there's like the copy on write handle, which you can edit or read from. And then there's the underlying object, which is copied when you write to it or when you call dot edit. But it's not like it's keeping track of whether or not you call dot read, because like dot read is just returning a constref to the object. But if you have like a single handle, then that is only a one reference count. And so basically dot edit does is it checks if there's multiple copy on write handles to the same object. And if there are, it just clones it. And then that way dot edit, you're always like the only reference to the object when you call dot edit. So you can't reuse the same handle in an expression in both an edit and copy context, because that's kind of like having two threads do the same thing. But what I realized is that that is actually possible if the assignment operator takes its parameters by value and you evaluate the right hand side before the left hand side, because then what you could do is you created a full copy on the right hand side before you actually go in and call the edit
You,
operation on the left hand side.
you better optimize the hell out of that, or you'll drown in copies.
Well, I think this is more of a correctness thing. Like,
I, I'm just saying, if your performance is 10x slower than C++ today, no one will care.
no, this could be pretty much the same.
But I guess then
I
you
think.
you have optimized away that copy.
Okay, so like let's say that I do a value on right hand side, because like basically what normally happens when I do value on right hand side and I take const reference in C++ in assignment, right, is there's an internal copy if I'm taking the parameter by const ref, and then that internal copy is happening inside the operator equals function. And then if I'm taking something by R value reference, then there's an internal swap that happens inside the operator function. But
Yeah.
if I take the parameter by value, then I'm basically doing the same thing. I'm
Okay.
just moving it to happen before the call to the operator equals, which means I can have a single operator equals for both cases.
Okay. I'm like, C++ has given itself its own giant pile of death worms it has to eat, and I don't think it's a good way to design a language, but it's been done. And then you're in there eating the worms one after another after another. I would
Yeah.
prefer to close the can of worms and put them away.
So another kind of situation that I was thinking of here is like, let's say I have like a map, right? So if you're familiar with C++'s standard map operator brackets, creates a like default constructed value, and then the assignment you could say if you have like map A parameter X equals B, right? So A brackets B
Yeah,
equals
yeah. You
C.
can write code in the doc if it's easier to explain people.
Yeah.
But what are you trying
Um,
to do here again?
so what I was thinking, right, is if you like evaluate the left-hand side of your assignment in a map, right,
Yeah,
you'll you'll create like a default constructed value and then do an assignment to that default constructed value.
yeah,
So if you throw an exception while you're evaluating the right-hand side, assuming you did the left-hand side first,
yeah.
the map still contains like a default constructed value in that cell, even though you threw an exception trying to evaluate the right-hand side. So, but what I was thinking is if you evaluate the right-hand side to completion before you evaluate the left-hand side, then if you throw an exception while evaluating the right-hand side, you don't even construct a like empty value in the map. And so the map would be like unchanged if you had an exception while you're in an assignment, like evaluating the right-hand side of the assignment.
I guess the kind of the downside there, like the from a correctness standpoint, yeah, picking up through as a move effect or picking up by value, the right hand side does make sense. But then yeah, you definitely do need the optimizing compiler to
Oh,
realize that if you're doing copy from right hand, like you have a on your right hand side, you essentially have a reference to somewhere and you're assigning it to a reference to another place, that it doesn't end up being compiled as copy from the right hand side to stack and then copy from the stack to the left hand side.
so I
So
I
you
I,
can,
I tackled operator assignment a different way, which is to say, if you had a dictionary assignment, then I just declared it was a dunder method, like a Java, a Python dunder method that had bracket equals as the entire operator and then just evaluated to collection assignment. And then it's a function call. You evaluate arguments left to right. If one of your arguments throws an exception, that happens before you ever get into the operator, into the, yeah, operator for the dictionary. I guess it's a 3-element dictionary here. It has the dict, which you would normally do as like a method call syntax. But the concept here is basically there's not a R value, or sorry, you don't get a ref into the middle of the dictionary as a partial in-between state. You either have all values present and then you start doing the dictionary update, or you don't.
But now, like, if your dictionary is a hash map and you find that it's
Yep.
full, so
Yep.
you like there's no room for key.
Yeah.
Does that mean that you end up allocating before you figure out if value is going to throw an exception or not?
I would start by saying I got value. Yes, value evaluates. And then normally dictionaries don't throw, they expand. But if you have a fixed size dictionary, then yeah, then it evaluates the argument. And then you're
I mean, when evaluating value,
Yeah.
like let's say evaluating value throws.
Right. Then you don't bother to know that the dictionary was full or not because you died before you got there.
But you're evaluating left to right here, right?
I normally would evaluate left to right. I would say, compute, give me the dictionary. So the dictionary may be full or not, but I'm not calling
Yeah.
an under method on it yet. I just have a dictionary.
Okay, so you do perform effectively. You do perform you do what Ryan was here suggesting or thinking about, that value is taken by value, not by reference. So value here, when
Yeah. So
when
in
it's being passed in, it's already an owned copy effectively. Like you can't.
Yes, by the time you get into
This
the
cannot turn
dictionary,
into a situation where
yeah. This is the part of the ownership model for C++ that drives me nuts, which is fine. I don't have this in a non-ownership model like Java. In an ownership model, yeah, you would have an owned copy that goes into the dictionary because the dictionary is going to own it.
Yeah. And then you just need an optimizing compiler to if possible, destroy or optimize out the intermediate copies of.
Yeah, yes,
So
and
if
all
you
these
can
things
actually-
you do by values with things that are complicated. You better have some copy optimizations going on. Yes.
Yeah. So, another kind of like thing that I'm thinking of though is like, I guess if is like the default kind of implementations though, because like I think the method call approach is like definitely pretty valid, but it's almost like you would want to like grab like you would want to detect in this case like I have operator assignment and the left hand side is an operator brackets and I want to like make that a compound operation and like say okay if I find an operator assign and the left hand side is an operator brackets then that is now actually some kind of compound operator on
Yeah.
the thing and then it's like taking both the parameter and the right hand side and like fusing them into one operation.
That's how I've been doing it. Yeah. So if you're saying you have an array with plus equals operator here. So just go back to let me start this share again here.
Well, yeah, that's the way C# does it. So C#, the operator, brackets overload, is a getter setup property method. So you actually have a get and a set on it.
Yeah,
Yeah.
I like that a lot. I plan to use that in my language.
So I'm thinking maybe what I should do is I should like create like operator brackets equals, and then that's like its own operator that like before it tries to do operator equals, it checks if the left hand side is an operator brackets, and then if it is, it looks for like an overload for operator brackets equals, and then if that fails, then it starts to resolve the two separately, like operator equals and on the result of operator brackets, but only if the like operator brackets equals doesn't like resolve to a valid function.
For operator overloading, not sure if helpful, but the way Rust does the bracket operator is via the index trait, and it evaluates the left-hand side, the brackets operator to the end, but it returns just a pointer or reference to the location that it evaluates to it. And now you have two variants. You have the unwritable or const reference and then mutable reference.
But you get a
There.
reference middle of a compound structure like an array.
Yeah.
Yeah, the Java GC experience, not Rust does GC, so it doesn't count, was that it was a bitch to allow the compiler to have pointers in the middle of objects, because if the GC moved things, it had to move the pointer into the middle. And then these pointers to the middles could get far and wide removed, and it was difficult to track them. And C2 could do it for a very restricted case where they never left a function, and C2 is responsible for tracking the base of the array. And at GC points, he basically converted, array base or the index to the base plus an offset. GC ran, moved the base, and then he reconstituted the offset. But arbitrarily allowing an interior pointer to escape around, like, played havoc with GC. So Java just said, no, can't do it. And the GCs and the JVM said, no, can't do it. And of course, C++ likes to do that all the time. So,
Well, I mean, C++ doesn't have a garbage collector, so it doesn't have to deal with that kind of thing causing a problem.
But you get the safety equivalence problem. I have a pointer into the middle. If I happen to also know the base, then it was easy enough to verify the pointer in the middle was in the middle and not off the end. Or if I deleted the base, the middle guy was invalid now, and I better not dereference him or whatever. There's safety things you can do that they're difficult to do if you have these interior pointers, unless you track with the interior pointer the base of the object in question, like capabilities and the like.
C++ must still have that issue with the reference counting, or they must be reference counting the base plus the offset, because there's no other way to do it.
Yeah. And
one kind of place where you can get this problem in a native or statically compiled language, if you don't have a borrow checker, that is so if you compile or if you perform the dictionary lookup, the offset lookup, before you evaluate the right-hand side, and then evaluating the right-hand side actually goes and shrinks your array, something like that. Now you're out of bounds.
So I checked C++. It looks like the compilers actually do evaluate the right-hand side first as well. So maybe that's what I should do on mine. But the one thing that I do is a little different. What I've been doing is like when I call a function, right? Or basically there's what I call the pre-argument evaluation step. So basically it evaluates the expressions as you pass them, and then if they need to be converted to another type, it does the conversions as like a second step after the first step is done. So first you evaluate the expressions and then you do the conversions afterwards. But I'm wondering, like, should things happen in a slightly different order in this case? Or should I keep doing it this way? Should I evaluate the conversion on the right-hand side before even starting to evaluate the left-hand side if I'm doing an assignment? If like a conversion is needed, especially like a copy conversion.
I guess like from a safety standpoint, if there's some way that the right-hand side conversion could somehow magically go and shrink the left-hand side or move what the left-hand side is pointing to, then yeah, it would be safer. But that's probably a fairly weird case.
So one thing I've kind of avoided doing is like each time there's an operator, it does like evaluate all the pre-arguments before it does any conversions. But to not do that, because like it evaluates the pre-arguments, then it does overload resolution, then it does conversions. So if I want it to go happen in all in one step, I need to like evaluate arguments, but without like generating code for them, like figure out what type it would hypothetically be, and then select the overload and then generate the code. So I'm like executing the whole generation code path basically twice instead of once. So that's the reason like I've so far like avoided doing that, is because I have to like do this hypothetical generation of code to just throw away the result of that, and without generating any code to
Symbolic.
know like hypothetically
Yes.
what type it would be.
This is my exploration with type analysis is constant propagation. Lets me get the types of those things before and then decide I'm converting or I'm not in one go. It dodges the second pass.
Symbolic execution, kind of.
Yeah, the constant propagation is already effectively doing partial evaluation. So I'm already
Yeah.
doing that at parse time. And oh, look, it covers these cases where you need the parser needs to know something before it begins to emit conversions. I haven't tackled generic overloads. AA does generic overloads with Hindley-Milner and can handle all kinds of shit, and it does it in a nice way, except that you had to do Hindley-Milner. So if you fail with Hindley-Milner, you get these horrible error messages. Fine. I'm certain there's a way to do function overloading, operator overloading, no, function overloading in the type analysis game and get the same kind of benefits where you don't have to like revisit things 3 and 4 times and trying to figure out who does what order do I do. Overload this. If I convert, I can overload this way, but if I don't convert, I can overload that way. And I have 17 ambiguous overload options. So I'm hoping I can get that sorted out with this constant propagation approach.
And
The one
this
thing
is why
about
some people think that the correct choice is to never ever basically coerce anything to anything.
I'm mostly there, kind of. I'm allowing floats to go or inst to expand to floats. AA actually doesn't do that. He says, I do operator overloading and I have a plus. It takes an int and a float. And then I only have to solve operator overloading. I don't have any conversions. It's all good. All right. Yeah, Levo, go.
the one thing I really don't like about C++ after writing a small library is I have a lot of types that should implicitly convert to other types. And when I use some places, it'll just be you have like 5 different overloads that it can be. And all I have to do is just um, explicitly name each and every of the types that it can overload to in every class that can overload. Um, it's like a multiplication for all the types that from the from and the to. I have to explicitly name it. I'm like, why can't I just say these are equivalents? Like,
Can you go to some common type and then out again? Probably and not be safe or sound or something.
well, the what I was doing was I had an array, a string, and a string view
Uh-huh.
all be convertible to um, a span, which is okay. Actually, the easiest way to say it is I have a string view that will always have null and a string view that will not have null. And the array can, if the array is a car, it can implicitly uh, it can
Convert.
implicitly cast to it.
Yeah.
So I have to write the overloads for all 4, but yes, the basic type to convert to is the basic type that I want them all to convert to. So I have to do that one, and then everywhere else is like it's going to be fine as long as I use the base type. But getting to the base type is the problem.
The general rule of auto conversions is they apply everywhere, and yes, they go quadratic or whatever. They multiply very rapidly as the set of things it might be. And then you suddenly don't realize how how the compiler chose to get to from here to there. I don't know. I find them less readable.
So I pasted the code in the docs. You might want to screen share.
And then Cameron's trying to say something. Ah, there's some code. Yeah, let me screen share while the Cameron go.
So Cliff, I'd encourage you to not call what you're doing in AA operator overloading. That term is so terrible.
AA.
What you're doing is operators. What C++ does is operator overloading because it has a bunch of hard-coded functionality, and then it has a completely separate system for doing overloaded functionality.
Oh,
So
I
it's
see.
only overloading because it's both. It's this duality of I copied this design from C and then I hacked on this bullshit on top of it.
No, I
Where,
have
where in
basic.
AA,
Okay. All right.
where in AA, you designed operators to be implemented. So it's
Yes,
not overloading.
I
It's
see. I have,
hey,
yes, I implement operators, and as normal functions, like all other normal functions, you can choose
right,
overloading options with them.
right.
Yeah.
Okay, fine.
I
In my
always thought it
language,
was called.
Well,
I thought it was called operator overloading because you could override plus to append to a list, delete your hard drive, and make changes to the universe. So it
right.
overloaded what it did.
Yes.
so
You can't replace the plus in AA uh, from this at the point at which you replace plus, the code that you execute thereafter will see the replaced plus. But code that comes before you knows what plus is, and you can't force somebody else to eat your overloaded plus. So you can't harm other code, if that makes sense. Like a library that's compiled, it will take the base normal plus. Your code, you wrote a new plus that says kill me now, and maybe it adds and maybe it doesn't, who knows. And then you call a bunch of stuff. Well, the libraries have a normal plus, but your own code can kill itself. That's fine.
well, for my language, the like if you do plus, it's just looking for operator plus on whatever the type of the thing is.
Yeah,
So
yeah,
like there's a built-in operator plus for int32, but
yeah,
if you have your own custom type, you have if that operator plus doesn't exist, then you just get a compiler error because there's no
yeah,
operator plus for your type.
yeah.
So
That's what goes on in AA. Yeah.
yeah.
All
But
right, so let's look at what Levo's doing here.
you can't override like primitive operator plus in my language, like those are built
Right.
in.
Yeah, I can't override it because I by design it's not actually built in. It's actually part of the core library, um, but you can make your own
And
plus, which
that's
extends the original
all right.
plus that
Just to
gets
be
it
clear, Cliff,
overridden.
that's why I was counseling you to not call it overloading
Okay.
because the operators are actually defined in the language.
Yeah, they're defined in the language. Yeah.
Where C++ has, oh no, we hard coded that into the compiler and then we let you define them in the language as well.
As well. Yeah, yeah.
Wait, but you cannot redefine the primitive operators like for ints, if that's what you're talking about.
I'm sorry, which ones?
In C++, you cannot redefine operators for the built-in types like ints.
Oh,
So
I
that's
see.
so that sounds exactly the same so far from
Yeah,
what I heard.
Wait,
right.
can't you?
Yeah,
My
I bet.
implementation says I have a primitive int and a primitive int plus, and then by fiat I say you can't override it, which gives me the same situation that I think C++ is
Yeah,
at.
that sounds exactly like C++ so
Yeah,
far.
yeah,
I think the only difference is that in Cliff's case, the definition of the standard plus is in the standard library, not in the compiler.
yes.
So
Yeah,
the
and
standard library is blessed in some way.
it uses a blessed primitive that can't be written by anybody else. So yes,
Hmm.
it has a new syntax that says here's the intrinsic that you get out of it.
Yeah, for what it's worth in Swift, that's also the approach, and even the built-in types like ints have defined operators also as part of the standard library.
In the
Yeah.
original implementation of our library, we defined the plus operator using basically half adders. So we did bit arithmetic to do the addition. So obviously it's possible to write it in a language, but you would never want that code to actually get used.
Yes.
Maybe you want to add some carry propagation optimization.
Yes.
I'm
All
still
right.
ready.
So
Let's. Are we ready to pivot to Levo here? You got a register allocation bug?
Okay, so all week I've been thinking about register allocation, and then the other day I saw an article about it. And the one thing about register allocation is everything talks about it as a graph, and graphs are not that intuitive when I try to solve a problem. So I was thinking about how would I solve it if I'm doing some kind of like tree allocation. So let's just take this example. Just let me know if someone has tried this before and how many ways this is a bad idea, because I'm sure it's a bad idea. I just don't know how
Well,
it's a
let
bad
me preface that all register allocators are heuristics, and they all do better on some things and worse on others. And it's really more or less about how broadly your idea compares to across a broad corpus of things. So the fun thing about retroallocators is you can always go implement one, and you can always keep adding heuristics indefinitely. And if you have a large enough corpus, you can just keep fiddling and homing in on improving the corpus you have.
I have an IDE as a blocker, so it's going to be a while.
So retroallocators, I'm saying, are never, they're never done and they're never right. They're never perfect, but they're never, they don't have to be bad either.
Okay, so
There's an infinite playground there.
this is what I've been thinking. So at the start, when you go through the function, and this is assuming you optimized like a lot of things already.
Yeah, you're into the retroallocator phase. You're done optimizing. You've done things. Yeah.
So like before that, okay, right at that point, you can just go through all the basic blocks and say this is going to run 10 times. So I'm going to score this as a -10. Or actually, let's just do positive. This is a 10.
Yeah.
This is going to be a 0 because
Okay. So you're allocating frequencies.
Yeah.
Okay.
But
So let's allocators
not
frequently do things with frequency. Call it freak
Okay.
here 10, which
Yeah,
is hot code.
So this is not actually for the resters itself. This is just which block to look at first. So since this block here, it only executes 1, we can give it a 1. And then here, let's just say 50% of the time.
Yep.
I'm not sure how you want to denote that.
Well, I usually said
0.5.
1 point.
All right. So here it's going to be 100. So
But times the frequency of 0.5. But you can go either way here. It's either 100 or 100 times 0.5, which would be 50, depending on how you want to think about life.
Yeah. So one confusing part was like if I don't know what the variable is, I don't know if I should score it as 1,000 or it really doesn't matter what number I pick.
No, all loops with unknown bounds get a 10 as a dumbass heuristic.
Okay. So in this case, what I would like to do in my made up raster allocator, I'll wait until you're done typing. Yeah. Okay. So I would want to do the most frequent block first, which would be this block because it'd be 100 times 10. So this has a score of 1,000.
Yep.
And to make it simple, I'm going to assume that this block does not spill. And then we look at the next most frequent block.
Yeah.
That would be this unknown one here, and we can handle that.
Yeah. This strategy has been tried in the past. It can be made to work pretty well. It's all fine.
This is effectively what LLVM does. So LLVM's greedy allocator basically just picks a priority for every node or for every like live range, and then says, okay, these are the ones that I really want to allocate. Whether that's not necessarily just because the block is high frequency, but because something lives across a lot of high frequency blocks. Because usually you want to account for like, I don't know, some variable that gets used everywhere. And so it's not about it being used in the hottest block. It's about it being used in every other block that is the second hottest, let's say. Things like that.
Does GCC happen to use this as well?
No, GCC just has a graph coloring allocator.
Okay, because last week I caught GCC and LLVM both doing really bad raster allocation, really bad ones, and that's what got me thinking about this.
So the trick with really bad on a single case is that maybe you want to attack it, but you must verify your changes over a large corpus because there's really a game of whack-a-mole goes on. You fixed this guy, but then you broke 10 other places elsewhere. And just as a for instance, I have this cool heuristic that fixes this problem. You better check that you don't break 10 other places when you fix this one.
So I have a question. Why do you say that the allocation that you got from GCC is bad, though? Is it where you're looking at?
Oh, I wanted to say why. Okay.
Yeah, say why.
I had a literal that was 8 bytes long, and I saw that GCC loaded it. Then it used the register once, and then reloaded it with the same constant, and then used it once again.
Yeah, sounds.
And that register was not touched. Like the only time that register was touched in that entire body was when it loaded it twice and written to it twice.
So
Like,
I think this might be a little bit of a misconception, right? Because if it uses it once and then writes over it again, there's no dependency. So like there's register renaming and all sorts of things. So I would not like assume that GCC is doing something wrong, because like the way that the code executes on the CPU is not the way that your assembly is loaded out, because there's what's called register renaming and all sorts of like pipelining stuff. And so these compilers usually are pretty smart about that kind of stuff. And so just because it looks bad to you, you're kind of looking at this from the lens of like, oh, the CPU reads a single instruction, executes the instruction, then moves on to the next instruction. But that's really not what happens. What really happens is the CPU loads 10 instructions, does a bunch of register renaming, and generates microcode for those instructions, and then executes the microcode.
Yeah. So let me back up for a second. I put a little chunk of code in the bottom. I heard Levo say, I load a value, I did something, I loaded it again, I did something again.
Yeah,
Quick correction, very quick correction, no microcode. Do not confuse micro operations with microcode. Those are entirely different things.
Okay, sorry.
Microcode is how you wire things in hardware.
Yeah.
Micro operations are those small operations, not necessarily small. Some of them are one-to-one to x86 instructions. Most importantly, micro operations have absolutely nothing to do with RISC operations. There is no relation with RISC CPUs, and there is with the micro operations on x86. Completely different things.
Right. What I meant was that it's going to load all your instructions and then convert those to micro operations, not micro.
Yeah.
I think going back to the example. So if Levo's example does look like that, where there's nothing going on between the two places, which I'd actually be curious what the example looks like, because if there is things going on in between, it could be that like, oh, something just gets clobbered.
Right,
so it just says, I'll like it. I'd rather rematerialize than reload or something, or than preserve the range.
Right.
But if it is just like this, then you would basically, the register allocator shouldn't split them up.
Well, also
it
actually
can split them up, as in like it might get it wrong, as in it thinks, oh, this would be a good thing to split, and it's like, not really.
It may also be faster to load it twice because of register renaming, right? Because the registers that you use are not the actual registers that the CPU, because of register renaming, right?
But if you could just avoid renaming a register, that's still less cost. The cost of renaming is like, it is part of your pipeline, so it's not really a cycle.
Yeah.
And then so just preserving the register is also like doesn't really like. You basically, for everything else, it evens out except for the cost on iCache, where you'd rather just like not burn the extra bytes.
Well, what I'm thinking of here is like, what if there's a situation where it's like, oh, if I reload this value, that register is not actually used, so the CPU can use the register for something else, and that maybe that's
the CPU can use it for. What do you mean when you say it?
So let's say like because let's say that the CPU sees that a register is read once and then it's not read from again before it's written to. So after it does that one use of the register, it doesn't need to store the value, and so it can just reclaim the physical register that has been remapped and use some sort of register renaming to like reuse that physical register, even though the instruction register might be.
I think you're stretching really hard to get a gain here in the example as we have on the screen, which is admittedly very lean.
I know.
I would rather go more concrete if Levo can say something. You saw. Can you do that, Levo?
I just got reproducible. I was just trying to figure out what's the latest architecture for Intel, but I just put in Skylake and I saw that GCC produced it. Cliff, I'm gonna put a link in the docs.
There's some code. Let's go look at code.
So I'm pretty sure that's multiply doesn't clobber the variable, but maybe I just remembered wrong.
Okay, so I see code on the left. We're in the middle.
So look at 4 in the middle column, the GCC one.
I'm sorry, look at 4?
line 4.
Line 4, move RSI something horrific.
Yeah. So RSI, it's only used as a source register, and
Yeah.
it's never written to. Yet line 31, it reloads the constants to a different variable, and it just made no sense to me.
Okay, no, this does make sense. So the reason why is because here's the deal. There's going to be a line that you cross where you have to go start pulling out callee saves and do spills and stuff like that. LLVM and GCC here are just trying to avoid that point because let's see, out of the total number of registers you're using, we've got like R9, R10, we've got RDI, RSI, R11. Like we've got basically all of the ones that aren't what's it called, that aren't caller saves.
Oh, you're saying he force a spill if he picked
to avoid
another
using
register.
callee save.
Yeah, it could be.
Yeah, because it looks like every other register is being used up until the callee saves, and if you wanted to use a callee save, now you're doing a spill, and it's like, well, I'd rather rematerialize than spill.
I think what he's saying is that RSI is not used again before that point.
Well, it's used. I'm trying to highlight them. It's clearly used a bunch of times.
Yeah, it's always used as a source, as far as I can tell.
Double click on RSI on the RSI text, it will highlight.
Yeah. Destination is on the left in this syntax, right? This is the
No, it's, yes.
So
it's that constant you get by length n7 times 8 minus 1 shifted. It's some giant bit mask. But my guess is where it's coming from. Okay.
Yeah, so
LLVM bit mask. Yeah,
does not have this bug, and
it's
not a bug, but
I think this happens because there is a branch, and GCC has decided that maybe there's like a micro op that if it sees that in the same code path, like when you after a branch, maybe like
I'm with Yasser. I think the obvious answer is it ran out of registers, and the options are spill it or rematerialize it, and then you rematerialize.
But no, it's not reused. So that register is not reused. So,
I'm sorry. RSI is used and used and used.
Yeah,
why doesn't it come through again? So he jumps to, that's the loop. Why doesn't he take it out of the loop? Because it's live out of the loop. That's a good point. It is live out of the loop. Yes.
Yeah.
Okay.
So
I don't know. Wait. Okay. So you're saying that
it might
client
be more
didn't do
clear
that.
if you look at the source of the C++ source.
So here's Clang using Rax. Yeah, Clang keeps it alive and uses it after the loop exit.
Yeah.
Yeah. No, I think you're right. I think there's been a rematerialization glitch there.
Yeah.
I would benchmark this because it could. I'm not saying that it.
My best bet is that they're going to perform exactly the same, but that's a speculation.
Yeah,
this is one cycle. Like if we're talking about like iCache costs, iCache costs happen when you have like a megabyte of program.
Yeah.
Okay, here's how I noticed this. So last week there was some kind of article about using rep move for memory copy. I don't know if anyone saw that, but
every other generation, it's a good or a bad idea. Fine.
Yeah. So and I remember that my hashing code did not. This is murmur hash. I just call this mine because I use it in my. It's a public domain, so I just use my source. I remember this not inlining because it didn't want to, mostly because of the mem copy and whatever reason it just didn't inline. So I want to look at it again, and I wanted to measure rep move, and I noticed that rep is actually really, really slow. So I tried mem copy.
You got to change your generation from tick to tock.
Yeah, and I tried mem copy, and I just assumed that mem copy would be fast, but it turns out if you unroll, the original code had everything unrolled, and I just looked at it and I didn't like it, so I tried having a random input, and then I noticed the mem copy was faster, so it went from slower than the unrolled to faster to the unrolled if I put if I had a random length, and then. Just benchmarking, I noticed the difference between the GCC and the Clang, And I thought, this code is simple. Why isn't it producing this exact same code? And then I noticed the rematerialization. It's only like 2 cycles, 1 or 2 cycles difference. But I noticed it because I was just like happened to look at the benchmark for this specific function, and I just noticed a number of difference between client and
This is one of these games where you badly want to only look at large corpuses to fiddle. Like if
Yeah.
you're getting 2x speed ups or slowdowns, then you can look at a single method and determine what to fix. If you're getting 0.1% variations, you can't statistically measure that without like
Yeah.
a giant corpus.
I don't think anyone's going to notice the 1 or 2 cycle difference unless they just happen to be micro benchmarking.
Yeah, exactly.
Yeah, it's even barely like a cycle to rematerialize the thing, because
Yeah.
you can decode multiple instructions a cycle and you can rename multiple instructions a cycle. So it's probably like not really going to show up unless you're like starved for
Right.
ports or something.
It literally might come down to you have a tiny bit more or less iCache, but you really would be shit like, hey, the loop border slid up or down and how it landed in memory. And now the loop border has a middle that spans a TLB page. And now I'm taking, I can't prefetch across the TLB page or something. I mean, there's all kinds of silly things that happen that you have like so little control over that can make a huge difference.
Also, like it can be the case that the CPU is like doing something in micro ops that is not the same as what the code you've written is. So you don't actually like, it could be like there are certain sequences of instructions that actually get like micro op to the exact same thing, and they're different, but in the assembly, but on certain CPUs, it's like actually exactly the same when it actually executes.
Could be the same, could be wildly different. Yeah.
Okay, so let's go back to my rest.
Yep. I think we've mined out that one.
Yeah.
Let's how long is that Gold page won't stick around though? Okay, fine.
Yeah. So let's scroll back up so I can see. This. Okay, so I forget where we were, but
you were like, "Hey, I'm going to allocate in the hot loop."
Yeah.
And then I'm going to allocate the second hot loop, and then Yasser said, "This is what LLVM does."
Oh, correct. Yeah. So now I was thinking that according to score, it should be that loop inside of 50/50, since that would be the most frequent, the next most frequent.
Probably. Yeah.
Yeah. So I just threw in the branches.
Yeah.
Make it
right.
more
So this will
realistic.
be, let's call this, 90, 10.
Yeah.
Times the outer guy, which is 50, as a for instance, right?
Yeah.
Yeah.
So actually, I think I'm meant to put a break in the else, but it doesn't really matter for my example. So
sorry, I'll get there in a second here.
Yeah.
I'm sorry, where'd you put a break?
Yeah, I was thinking about putting a break in here, but it really does not matter as long as we just decide this is a low likelihood for whatever reason.
Yeah.
So what I was thinking for restore allocation is I'm surprised you can hear that. I mark all the functions. So I try to color everything in the most frequent block first.
Yeah.
And whatever variables that escape or that is still being used, I would mark. And I figure I could just, I would do, okay. When I said start at the most frequent, I mean I would start at the for loop. Maybe I should just put my mouse in.
The concept of inner to outer or hot to cold is well known in register allocation land. And you always have the cleanup at the edges things that you have to do. But this is a well-used strategy that it certainly works well enough in some cases that, that people like it. Graph coloring guys don't pay attention to blocks during the coloring, but you never color the first go. So you spill. The spill heuristics for graph coloring guys plays exactly this kind of game.
All right, so I just wanted to make sure I'm clear that I wanted to start here as the most frequent and then do these.
Well, you do the 10,000 down below.
Oh yeah, I meant as the third one.
Yeah.
Okay.
Yeah.
So I figure that by the time I get here, I can just eliminate a lot of resters, and then I don't have to. I probably should have started that. I'm assuming that everything's in SSA form, and I have unlimited resters.
Yeah.
So here, I would just eliminate a bunch, and then in these previous
When you
blocks,
say eliminate a bunch, you
I mean
mean
it's
you
already
assume that the
colored.
registers are dying because you've done some computation from the loop and the set of live values shrinks.
Yes, and
That
the
is a
only
common
thing,
scenario. Yes.
yeah, and the only thing I would care about here now that I colored it is the inputs.
Yep. They'll have to be right. They'll have to get registers, and but you've picked the inner loops, and now the outer guys on either edges, the result value and the inputs wants to marry to existing live ranges that have been colored, and so they want to, to avoid copies, you want to give them the same colors. This is a standard thing you do with like linear scan guides.
Okay, because everything I've been reading, it's talking about creating a graph of everything and then figuring out, like looking at the largest, like whatever is the largest as a live and splitting it. And it just seemed weird
Okay,
because,
so let's break up things a little bit here.
yeah,
So if you're a linear scan, you don't typically build a giant graph. If you're a graph colorer, you do. Okay, fine. The graph for the graph coloring is a Boolean function. You color or you don't. And then out of that is a list of things you failed to color. But if you colored, you had no spills. None of this matters because there's no spills. You're done. But you typically don't. You spill. Okay, now you get to the spilling logic. Same for linear scan. You have to do something about things, and you want to pay attention to frequency about where you're going to do it. Linear scan doesn't go through these rounds where I say I split these giant live ranges. Instead, I'm going to build up things piece by piece, maybe inside out like you're doing here. And so your live ranges are all effectively chopped down to a basic block or less. You allocate within a block, the hot block, and then you look at the borders of the next hot block, or you're done with the loop and you're looking for the border from the loop to low. And at those borders, you have to mesh things up and you'll start getting your spills where you have to have them at the borders, which are outside of the hot code, which is what you're looking for. The thing with the graph coloring doing spilling logic is you actually, well, at least for me, certainly looks at the frequencies and chooses to spill around the hot loops, getting the spills roughly the same spot you're going to get them out of your linear scan.
that's actually why I wanted to put the 50-50 branch, because I was planning to like talk about spilling and putting it in between the for and the if.
Yeah. Yeah.
So maybe I didn't read the papers in the right order, or
there are a lot of old register allocator papers and a lot of cool ideas, but they're scattered around. There's a bunch of them. Yeah.
Yeah. So the one thing that they barely mentioned frequency, so that's one of the things that confused me.
Okay.
A lot of older register allocator papers worked off of like static heuristics. I know that Briggs's thesis, for instance, like doesn't really mention block frequencies. It just talks about it as like loop nesting depths.
Yes. You approximating. Yep. Absolutely. Yeah. And in fact, in your code here, you mostly approximate all loops as frequency of 10, which is the common heuristic that people use since the 80s. If you have a number like 100, you take it. And if you don't, it's just 10 and you scale.
Oh, okay. So when all the a lot of papers in a lot of places were saying that the register allocation is really expensive, just because you have to build the graph and do all the
graph coloring. So you say register allocations, break it apart. Linear scan is typically can be made faster than graph coloring, typically gets a worse allocation. Graph coloring builds a large graph. That's the expensive part of that. You optimize hard to make that big graph not so expensive to build. It can be made pretty damn cheap. It's still more expensive than a good linear scan. But as C2 shows, it doesn't have to be super expensive. You can make it super expensive. People fuck that up all the time. But you can make that big graph fairly cheap.
Okay, so let's talk about why is it expensive?
Because it's n squared.
It's n squared.
Yeah. It is an interference between every program point to every other program point, combined into live ranges. So it's every live range to every other live range. But the number of live ranges you have is the number of interesting program points, roughly divided by the number of registers or whatever. You get a lot of live ranges. So
Okay, so let's take the 50/50 loop.
yeah,
In that loop, I do not care about the registers inside of the hotter two loops below
yeah,
it,
exactly.
and I probably don't care about the registers before the if statement.
Yeah, right.
So when you say n squared, there's a lot of registers I don't care about, so it's just
Yeah.
confusing that it's n squared.
Okay, so that's graph coloring, not linear scan. The trick
Yeah.
with graph coloring is the entire graph colors or it doesn't. That means the entire program, inner, outer, every other loop is all chosen to color all at once or not. If you win, you no spilling and you're done. You walk away. And if you
So
lose,
Note that even in this kind of setup, it can still get quadratic pretty easily. So the way that would happen is not like, oh, because you see one block and you ignore everyone else. Well, the first block can ignore everyone else. The second block has to care about the first block. The third block has to care about both the previous blocks and so on. And you end up with this triangle shape. And it's like mostly quadratic.
yeah.
That's how LLVM ends up, because after you make assignments, you have to then account for those assignments with the later assignments. So even if they were in separate blocks, well, values can live across blocks. So you have to worry about that kind of stuff.
Is this a linear scan or a graph coloring from LLVM?
It's like a out of order linear scan.
Okay,
They call it greedy, and effectively it
oh,
just plucks live ranges and then just allocates
right.
them.
Because
This is
I've
priority
done a
order.
linear scan, wasn't totally out of order, but the scale factor was the width of the register set. It didn't have, and then times every basic block, but it didn't have to be multiple basic blocks. I just took values in the registers. I mean, that was how you did it.
Do people okay, so why do some people talk about both linear scans and register allocation? Do you use them both together, or is it generally separated?
Some people take either approach.
I definitely read some things that confuse one with the other.
Yeah, you need to sort that one out from context because I've seen them. The in the land of the Java, the JVM, the C1 compiler uses a linear scan, and the C2 compiler uses graph coloring. So here in the same JVM, there's these two internal compilers. One's linear scan, one's graph coloring. Which one is which? Who's talking about which one? You need some context.
Okay, so I guess the better question would be, would I use some logic in linear scan like logic in graph coloring?
Well, you get it. Yeah. The spilling has this funny property where you might want to think about it that way. I guess I'm not. I have
I
certainly
can ask a more specific question.
there.
The only thing that comes to my mind when I hear linear and graph coloring is when this SSA-based graph coloring paper, when you still have your program in SSA form, then this graph is actually a chordal graph.
Right.
And chordal graph is just an intersection of subtrees. So the complexity of this algorithm is going to be nearly linear. It's like linear multiplied by a very slow drawing function.
So I'm not using the chordal graph property in C2, but it is all in SSA form. I'm not using it in simple either, but it is all in SSA form.
Okay, so
I will get an n squared graph.
I should probably been more prepared.
No. This is, whoever watches this all gets to get a lesson in what the hell goes on with register allocators. This is a good basic stuff about register allocators. It's all good.
I'm also looking into like the register allocation prior art, and then for the chordal graph property of SSA form, I was confused
Link.
because
Hey, Matt, can I talk to you and get in a link for the chordal graph on SSA?
I was getting confused, and I was reading this one paper, which is like if coloring a chordal graph in with SSA form is like nearly linear, what exactly, there was a paper like what exactly is the NP complete part of register allocation? I don't know if anyone came across that paper. I can drop it, but I was reading into that this
Oh,
week.
it's known in P complete. The chordal graph property doesn't help in that sense. There are proofs that in fact I want to say it's hard NP complete. You cannot get an approximation to with any particular constant ratio of perfect. There is no algorithm which for all graphs guarantees you that you are within a constant fraction of optimal. So
The thing with the chordal graphs is supposed to be that if you're coloring them, you can color them optimally, but then you run into the next half of the NP problems in register allocation, which is what if you can't color the graph? What should you spill? And then that creates this big decision tree thing that's just like, I can go down only so many of these paths because if I go down all of these paths, that's exponential. It's like, I can't say like, oh, spill this guy. Then, okay, don't spill this guy. Actually, spill this other guy. Okay, spill both. Don't spill either. Spill this other guy. Stuff like that. And if you go through every single possibility, you'll eventually reach the correct optimal solution, but you will have walked this exponential route to do so. And so instead, we just like pick a route, and then we just say, keep making forward progress as you keep chomping away at splits.
yeah.
So this may be why it hasn't really seen that much adoption in practice in mainstream compilers.
The chordal graph thing.
Yeah.
Yeah, right. I didn't see very many people use it. I saw the papers, I've read them all. Like the graph coloring guy, at least he's easy to write the code for the graph coloring. In simple, it's like 30 or 40 lines. It's not that big. The spillings, of course, is a giant pile of stuff. But the actual, I'm going to color you, it's a relatively small thing.
So for spilling, I was thinking that since I colored most of the hot loops or the most frequent blocks, like the further away I get from the hottest loop, the less importance it is to get the correct spilling.
Right.
So
right.
I figured that if all the loops are colored and I have to spill, it really doesn't matter what I pick because if I would just have to put a fix up, like a reload the variable, or what is it called when you load a spill? Is it just load or?
I have heard fill.
That'd be a reload, yeah.
I have heard fill, like spills and fills, but I also also reload is used by LLVM too.
Yep.
Yeah.
I like fill, so I'll just say fill. So after coloring the do I say coloring if I do a linear allocation?
Yeah, you can say that. I mean,
you can just say allocation.
An allocation.
You have allocated a register.
Yeah.
Okay. So like I don't read all this stuff like every day, so it's hard to keep track of, especially when I'm reading articles that are not so good. It's hard to keep track of the terminology. But anyway, so I figured that if I color all the loops first, then I could just fill any variables that didn't get allocated that the loops need. And I would probably have to give some kind of score, not based on the loop, but based on it's going to be needed later. So like every time I do a fill, I probably have to give it like a score of like this, like every basic block that's going to need it. I'll just okay, wait. This is going to be wrong. I don't mean basic block because you can have one block inside of another. What I mean is in this basic block, I have like 3 children blocks, or what is it called? It's not called successors, or what's it called when what's the opposite of dominate?
Post dominate. The opposite of dominate is post dominate, but blocks
Is that the word you're looking
blocks.
for?
Okay, I'll just say children because it's easier for me.
Okay, wait. I don't know if that's the word it's looking for. What are you trying to say?
Okay, so let me type something.
Yeah, because post dominate would basically be all paths will eventually reach this point, and then dominate is all paths to me have gone through this guy, and then the opposite, basically.
Whereas what I'm thinking I'm hearing you say is the place where linear scan falls down versus graph coloring is when you have sort of complex control flow with middling frequency values. And this kind of I have a really hot loop or I have really cold code. Both allocators will do just great. There's an obvious place to spill. There's an obvious place to allocate. You'll get a good allocation in either case. Where it doesn't work out so well for linear scan is when things are a lot more muddled. You have a large soupy mess of control flow with medium frequencies everywhere and uses going all over the map.
Okay, if you scroll down, you'll see my blocks. Okay, so you can see A, B, C, and D.
Yeah, what's the parens between A and B here mean?
Some kind of like branch, like a for loop or if loop.
So there's some arbitrary code here.
Yeah. So so let's say I'm in the root. The roots. I should type it up. Root.
Yeah.
So I'm in the root block. There's A, B, and D. That's the children. I want to exclude C. So if I'm in the root, what do I call A, B, and C and D, but not
When you
C?
say you have a root block and A, B, and D come from root, you mean root branches to A or branches to B or branches to D? Or do you mean there's some control flow path from A that gets to B that gets to D? You always
For
hit
me-
D from A, you always hit D from B.
For me, it's easier to say children and excluding grandchildren, which would exclude.
But that's not, you didn't answer the question. Is there a three-way branch, roots running a switch statement, picking one of A, B, or D, but never both?
No. I want to keep A, B, and D, but not C.
Okay, so you have but you say keep, I'm still asking the question. I must execute A before B or not?
For what I'm going to talk about, it doesn't really matter.
Okay, I'm trying to build a control flow graph here because that will answer the next several questions that come along. And the obvious control flow graph is I'm going to execute whatever code in A is. Then I have some conditional on some code. Then I'm going to execute whatever B is. Then I have some conditional that may or may not execute C. And then I'm going to run D. And then I'm going to run some code after D. Is that a reasonable control flow graph?
Yeah. So what I want to say about spilling was I was considering that for keeping a score of what I should spill and not, I should, if A and B uses like Rester 23, I want to give Rester 23 a score of 2, but if it's
So when you say you're giving a score of 2, you have a use of some value, which you're going to give on register 23.
Yeah. And if I have if C is a loop,
Yeah, Val, Zulu. Yeah, fine. Yeah.
Okay.
Yeah, right.
So
yeah. Right.
I want to give Zulu a score of 1 because it's only going to be used once right here.
Uh-huh.
So if I'm trying to color the roots, I want I was thinking about having Rester 23 be have a score. Yeah.
The value that we're putting into 23 get a score of 2 because there's 2 uses of that value. And should it get register 23?
It's because I didn't type it up, and that's why I'm confused.
Yeah.
Because if I write it, it's easier. But anyway, even though Zulu's hotter, it's only going to be used inside of C. So I could just fill it here if I have to.
Yeah, you're filling it outside the loop. Right.
Yeah.
So some register allocators account for this kind of stuff is by measuring area, like the area that something is live in, and then how hot is the area that it's alive in.
See, that's
So
the
like,
thing.
how many uses do you have? Or it's usually like a measure of like how many uses, like the use cost, and then divide that by the area or some metric around that, so that if you have a very small area that you're used in and you're reloaded a few times, then it's like, oh, okay, that's less good to spill. But if you
Okay,
have something that spans a really large area and is used a few times, then that's like great to spill.
So
so
an example for the C2 and simple register allocator heuristics, callee save registers, caller save registers are live on entry, used at exit only. They have one def to start, one use at the end, and their area is the entire function. So they become ideal candidates to spill.
So the one thing I was like worried about is some things might score Zulu as high because it's in a hot loop, and I don't want it to be high.
Right. So you separate out the area from the use count. If you have a sort of more naive allocator, you would claim Zulu has this, an area that's B and C, but a use of 100.
Yeah.
And so it's actually fairly hot, and the area is not that big, so give it a register.
Yeah. So inside of C and possibly B, I would want Zulu to be kept because it's in the hot path.
Right.
But once I get back into the root node or the root block, I just know that I'm saying it wrong, and that's why it's painful to me. But by the time I get back into roots, I don't want Zulu to be to score high. I want it to be score high in C and possibly.
So you have it right now that it's dead after C.
Yes.
So if instead it remains alive because you have some use far down below, so the Zulu covers a large area and it's hot at the inner loop, you have this tension that says it's a large area, yes, spill, it's in a hot loop, no spill. And how do you resolve the tension? The answer is just spill it around the hot area.
Yeah. So how do other allocators and graph coloring handle this case?
Okay, so graph coloring only does it because of spilling. When you color, it doesn't care. When you spill, you care. And I've done this repeatedly, do it in C2, do it in simple, and I look for exactly uses in hot loops to decide to spill around the loop. So the standard heuristic going on in simple here is to say, I have a thing, it has a lifetime that spans some loops. I will split it around its first set of inner loops, and those inner loops may have more and more and more inner loops. It will first split around the outermost set of loops. That breaks the live range up into an area before the first outer loop, inside that first outer loop, between the next outer loops, in the next outer, and so on. So you split around the outer loops. And then I'll color it in. And if that still fails, and I go look at and the guy who I'm looking, who've already split into these smaller areas, he's also still not getting color, then he splits into ever more inner loops.
Should we cover splitting, or is that a big topic on itself?
It's a big topic, but we're covering it right now, whatever. If you're what I normally think of a linear scan that says, let's do a frequency-based linear scan, you start by giving the Zulu and C a register because it's hot in the inner loop. Great. Then you step out a notch and you've picked up the B block, let's say. He wants to have a use for Zulu, but and maybe you can give him the same register that's used in C, but then some time passes and eventually you get the last thing at the bottom of root there. And now this Zulu, who you're trying to match with other things, all the registers got used because Zulu wasn't around then. What do? Well, now you want to say, oh, I'd rather have spilled the last time I ran out of registers, throw Zulu to the stack, and then pick it up. So there's a spill between the bottom of C and somewhere in the D area where you ran out of registers. Zulu's not going to get used for a while, and you make a decision, throw it to the stack.
See, I think a lot of things I read just didn't explain how they would choose what to spill. They would just say whatever is most frequent or whatever is this or that. But
yeah. There's also a distance to next use is a very common thing. I have a set of 16 registers. They're all holding on to values. I have a 17th value I have to load right now. I have to throw it in my 16 away. They're not currently known to be in the stack. I have to spill one. Which one do I spill? Well, a common heuristic is to say distance to next use.
Okay.
What is the out of order linear scan? How does that work, the ordering, as opposed to this frequency heuristic?
I'm sorry,
The
the
short
out of
answer is that it
order linear,
stops being linear.
so the out of order linear scan is still, in theory, linear time. It's just out of order because you've essentially sorted the blocks by frequency. But it does
Oh,
a,
just doing it like blockwise. Oh, okay.
but
Well,
when
so
you
the
when
issue
you
the issue you run into is that if you start doing linear scan and you start and you drop what's this called? And you start allowing for lifetime holes, now you've got like this inactive set, and those things need a heavier query, and the number of things in the inactive set can grow far beyond like the number in the active set. So like linear scan is supposed to be linear because the active set is bounded by however many registers you have. So that's how
yeah,
many interference checks you need to do ever. And
right.
then basically because of that, you're always either you're
You're
either
in a register
allocating
or
one
you're in the
register.
stack.
Yeah, you allocate one register at a time, and you can expire at most n or k, I guess, and then you can at
Yep.
most do k interference checks, so linear. Once you start doing inactive set stuff, you start getting to like it can be quadratic, because if I'm in like three, like if things are inactive right now, it could be that 4 things are inactive. It could be that 20 or 200 things are inactive. Usually it's a really low number of like, oh, I'm in a block that technically doesn't interfere with this value. And so in practice, people basically always take like basically everyone's linear scan has lifetime holes because it's like really, really useful.
Yeah, it's really useful, right? And so, right, so they would climb up. Yeah, you're right. They could climb up the quadratic curve.
Yeah.
I've certainly done linear scan with holes.
So another problem I was thinking about was if I actually wanted to write out how I would graph color or allocate like a given piece of code. I noticed it's like a lot of work to write it out, and it's very easy to make mistakes. So I rather actually write code to do it. Um, I'm so I think I gotta do it before I can like be happy with some kind of implementation. But I was also wondering that since coloring and register allocation or linear scan, or is it linear allocation? What was the word?
Linear scan, graph coloring. Those are the two terms.
Okay, so if we do a linear scan to allocate it, I was wondering, is it really if I wanted to efficiently use spilling, does linear scan give me a really bad spill rate? Like, do
It's
I?
generally worse on sort of generic junk code than graph coloring. All terms are generic. It's all NP complete. There's all heuristics. Weasel words abound. On average, over big programs, graph coloring gets you a better coloring at a higher coloring time cost.
So, if would it be really confusing in code to do both linear scan allocation and then use graph coloring for the spills, or does that
Different people have tried all manner of things. You're certainly welcome to try. So you might decide that you can do all the inner loops in a linear scan. That's, gives you a great basic block coloring for the hot inner loops. And then on all the complex control flow, you want to say, hey, I want to use graph coloring here, but I have these chunks which are pre-allocated and they have these borders on the chunk, which I'm waving with my fingers, you can't see. And the borders say, I've picked the following registers for the following values, and I've used up all these registers internally, so you have to spill around. And that's a chunk like a call site, which has a very specific calling convention for what you do with registers. Well, here's a variant of one which has a different than the normal API. It just has, but you treat it like a call. It has a bunch of eyes in, bunch of eyes out, kills a bunch of registers, and then that's just a known WAD, and you hand it to the allocator, and yeah, graph coloring can handle that from there.
So I'm making the assumption that the reason why a linear scan is worse. I mean, there's no one example of why a linear scan might be worse than graph coloring. It's just.
Oh, I could definitely get some like indicative examples.
Oh yeah. Okay.
Yeah.
I want to see them, but I was like thinking that maybe it just depends on whatever heuristic you're using in linear scan. So there, like, it could just always be a different reason. It's worse
There's
than
the main thing is that graph coloring attempts an all-to-all coloring. So it has this global knowledge that linear scan never has. So when he wins, when he gets a coloring, he gets to take advantage of this global knowledge. And that's the trick where he gets to beat linear scan.
The global knowledge.
The
Okay.
global knowledge, because he's checking all things versus all things in this n squared graph.
Yes, sir. Would you be able to show the example like right
I don't
now?
think I could write it right now, but I could cook one up for you. Basically,
I'd love to see them, but yeah, I've
as
totally
Cliff
seen this
described,
happen.
basically it's like the linear scan, because it goes like step by step. So we can imagine them all as graph coloring. They just have
Would it be
different
better if you
heuristics
type it
on.
out?
Say that again.
Would it be better to type it out?
I can type. I don't have an example like on hand right now, but I can type one out in a bit.
Okay,
Like
because
probably like
you're saying
on
it's
the Discord or something.
Yeah, come back to the Discord and look at it on the Discord, because I'd like to see this on the Discord too.
I've seen a few laying around where it's like, oh, this is like especially bad, and like you can write heuristics around this, but all you can really do is like hide the problem. You can't really get rid of it.
Yeah, some other
Mostly-
program will hit it again. Yeah.
Yeah. So the main issue is that as you're stepping through, we can imagine all of these color, like we can imagine all register allocation as graph coloring, regardless of whether or not we're using Chitin's algorithm. You're just choosing different ways to prioritize what to color first. Chitin's algorithm says, I'm going to color the most colorable person first, and then just keep doing that. And then it has a metric on what colorability is, which is just like, oh, do you have less than k neighbors? Basically,
Yeah, you get it trivially that one. Yeah.
Yeah, because at that point you can say, oh, all of my neighbors can color plus me, and it, like assuming that all my neighbors are separate colors. That is still like a too conservative of heuristic, which is why Briggs was like, oh, yeah, we can say that, but then we can also say, okay, sometimes it's possible that your neighbors like actually have the same color, so let's even if we end up in those fail cases, let's not spill just yet. It doesn't mean, yeah, just because you couldn't color conservatively doesn't mean you won't color optimistically, or whatever phrasing you want. But essentially, what linear scan says is the priority metric is just the timeline of your program, which is like an entirely meaningless metric. Like the only reason it's useful is not because it's like, oh, this is like really good for quality. It just happens to be useful because it means that we can avoid some of the performance costs of building an entire interference graph, because we can build one on the fly if we can just walk them through in order. But like that colorability metric means that you will run into cases where you say, I've got some function call, I've got some thing that like I'd rather spill some guy, but I haven't even seen that guy yet. And so you can write chains of these programs. I think there's one in the original like linear scan paper that's just like, oh, this is like the super degenerate case. Where you can write chains of these programs that just like want to spill, but then the next guy, if they were to take their time to spill the next guy, they would be better off, and you just chain those together.
You can't tell what's the good thing to spill here.
Yeah.
The proof
the thing you'd want to spill hasn't been born yet, but like you'd really want to spill him.
Right. Wait, that makes no sense to me, because how are you going to spill it if it doesn't exist yet?
Well, because the thing is that things don't usually interfere, like things don't necessarily always interfere for their entire lifetime. So what can end up happening is guy A, who comes in first, is the guy who you see, because at that point you needed to spill. But like there are ways to reorganize a program where you could say, oh, guy A should what's it called? How would I say this? Guy A should spill, but not that much. Guy B should spill more. And we could do that as 2 rounds of a good coloring algorithm. Or we could do that as like if we just go through it and blaze through it.
That's
like,
right. I think we need the concrete example here, because I'm getting lost at what you're trying to say. You have something in your head.
I'll draw a diagram at some point. One sec.
Yeah.
Why is LVM still on linear scan and not graph color?
It's barely linear scan. It's like the greedy algorithm does just go out of order, so it's like basically just a graph coloring algorithm. In the same way that I mentioned, like, oh, it's all about like how you pick your priorities. They just pick theirs off of spill weights, basically.
I'm curious to see if people have. Surely someone has tried a graph color in LLVM. And don't call me Shirley, so maybe it's not true. I would have guessed, given the long history of LLVM and the very large count of people who do things with it, that there is a graph coloring in LLVM. That's an open question to the community. Is there one? No.
The surprising thing is that like it's definitely not the most popular one. So even if there is one, I'm surprised it's not like as prominent.
Right, there's no flag that says use the alternative allocator.
Oh, there are those. I don't know if I've seen a graph coloring one in those lists. The ones I usually see, well, there's one that is a graph dealing one, but it's like a different approach than Chitin's algorithm, which is the PBQP one, I think is what it was. It's like basically just a SAT solver.
Oh, the SAT solver approach. Holy shit.
That was this
Yeah.
partitioned Boolean quadratic programming.
Yeah, that one.
Quadratic programming is not that heavy actually. I used quadratic programming in different areas, and it's not as expensive as it may sound. I wouldn't characterize it as expensive as SAT solver.
I gotcha.
Okay.
What's the high level difference between quadratic programming and a SAT solver? For assuming I'm somewhat familiar with SAT solvers,
I would
like
actually
what
say
is quadratic programming?
I would say they are completely unrelated because quadratic programming comes from the area of linear programming in mathematics. Like if you have heard words like mathematical programming or linear programming, programming in this sense means solving a system of linear equations. And quadratic programming is often when the system involves equations that have quadratic terms, like x multiplies by x.
Oh,
So
I see.
I wouldn't even relate. I wouldn't relate
Right.
it to SAT
Okay.
solver.
Yeah, you said quadratic. I did not go to quadratic terms, but now that
Yeah,
you
it's
say that, it makes
different
sense.
quadratic.
Okay.
I have another gobbled link. I'm not sure why it's not linking, but
Oh, I see. I always do this.
okay. So this is just hilarious to me because this triggers a problem in both GCC and client. GCC is this is basically the same code except I replaced on line 29 on the very left column. You see the memory copy.
Mm-hmm.
So I had a loop. I just replaced it with memory copy, and so the GCC code I believe did not change, and it still has the two constants. It will reload the constants for no reason, according to me. But
RSI comes through, and yeah, it looks to me that RSI is not in crushed, so it should be valid with the same value there. Yes.
So
okay.
the reason why I wrote the code using the loop was because if you look at the LLVM code, it now uses push on 3 registers, even though before it did not.
Sure enough.
So that's why I was like saying I didn't like GCC and LLVM register allocation. I don't know what the problem is, but that's what just got me thinking about it.
The easy answer here is that it's all NP-complete heuristics. Some minor twiddle follow you down this path in the heuristics versus that path in the heuristics, and he had a little minimal, you hit a little bump in the minimal, in the very complicated curve of optimal allocation. You found a minimal or maximum, got stuck in a low spot. Happens all the time. That it's the whack-a-mole game. You get a little better here, get a little worse there. Okay.
I'm not assuming I can do better, but I do know that I don't understand this whatsoever. Like why
so
that specific heuristic.
I certainly stare a lot of these in the simple allocator recently where it's some stupid change and a little more spill code, a little less spill code, and where did it come from and why? Sometimes it's worth chasing down, sometimes it's not.
Yeah.
You want to really chase it down as you look at a large sequence of things and then you made some change and you look at the large sequence and on average there's worse spill. Then you come in and start picking a poster child. Why did this spill and it didn't before? So here, he's grabbed R14. No, he's using it all here, but in the prior go around, he's using racks or something. Why did he want one more register? So the real answer is, had one more thing live. What is the count of live things that we can see in this program? Oh, by the way, when you say he spilled, he also did this. Move dx to ax, move si to dx, move di to s. What the hell? What is this three-way shuffle going around?
I gotta look at the old one. That's so weird.
Okay. Here's the old one. So there's no push pops. There's no three-way shuffle either.
Yeah.
I think it's because of the function call. I'll go back to the other one with the function call.
Yeah, the mem copy produces a function call. Yeah.
Oh, that'll do it. You're correct. Sure enough. Because this will cause the calling convention, which will immediately spill a bunch of things. Yep. I mean, the shuffle. Oh, and the shuffle is there because he had to move registers out of the callee save preserve area.
Yeah, and then also I think because the RDX is, I believe, the third parameter.
Yeah, it's a parameter.
Yeah, which is also the mem copy's third parameter. So it's just like preempting that, I think.
Yeah.
I can't tell.
Why did this
Oh, it
not
is actually, because then it does the EDX, which is like and 7. So it does actually like preempt it by putting it on RDX originally and then doing the and on the already placed value.
Yeah.
If you look at the code after line 37, like from 37 to down, you don't see DI being used or SI or DX. I don't think DX is being used.
Those are all going to be clobbered.
Yeah.
Yeah. So it's like, why did it save it if it's not going to even use it after the call?
No, why did
Wait,
he
sorry,
say
what didn't you save it?
So at the very top of the function, it saves. It looks like it's saving DX and a few other things.
Well, it's saving. Yeah, okay, here he's moving DX to AX, not to save it, but to crush AX conveniently, I assume.
AX is not used after the call, except to be overridden.
No, he's took the original incoming argument DX, he put in AX because he wanted to use it to crush it, and it's dead already.
Yeah.
The AX is just an incoming argument. It's dead. Now, why did he push AX here? This I don't get.
Yeah.
And because he pops here.
Oh, the push AX that's because stack alignment.
Oh, okay, fine.
Oh,
if you push an odd number of things, it adds an extra, or like if you push an even number of things, it adds an extra push so that when you don't have the frame pointer on, because if you have the frame pointer, then it's 16 bytes. But if you don't have it, then a call is 8 bytes. Then it has to go, okay, I need to fill in 8 bytes again, and then a 16-byte rounding.
Yeah.
And so it just pushes.
Yeah, BX and R14, or at least BX is definitely used.
Right. And he's out of registers because the copy crushes things, so he needs to for BX and 14.
Yeah. I wonder why it's not in line, because there's an N7.
Which means when you go over to this code over here, you won't find 14 because it's call save register. So he doesn't want to crush it and spill it. So he doesn't have 14, he doesn't have BX, he doesn't have whatever. There's like 10 of them he doesn't have. So he's compressed into a small count of registers, which is why he ran out. And I got a question here. Why did this not inline? Why did the mem copy not inline? They're like GCC inlined it, right?
Yes.
Like here's the copy loop.
That's copy loop. Yes.
Fine.
Yeah. So this is what triggered me thinking about register allocation.
Yeah, sure. It's a great. It's a great topic. It's a great deal. Go play. There's an infinite amount of room to play there. And at some point, I should see if I can get a simple to spew out the same format for Godbolt. That'd be kind of fun.
Yeah.
You can see just how bad an allocation I'm doing now.
Well, if you do,
you can probably put a pull request compiler explorer. I know they are pretty friendly bunch of faults. There are a lot of, like even toy languages. I think that got some integration with that.
They have somewhere it has a list of languages. I've seen it. It's big. You're right. It's quite
I
long.
also added compiler I'm working on Godbolt myself. You can just basically check out the repository of Compiler Explorer.
Here's the list. I'm scrolling through it.
It's just a TypeScript project, and you can add your language by modifying just a bunch of configuration files. It's not that hard to add your own language.
Okay. Oh, Pony's on here. Holy crap. Wait, Scala? How do you get the assembly out of Scala? Is that like not the JVM based Scala then?
Maybe it runs the JIT. Who knows?
I imagine it just gives you the bytecode or something.
Oh.
So yeah, it could be Java bytecode.
Bytecode. Fine. Okay, yeah, I don't want the bytecode. Well, it didn't help me. I lost it now. Yeah, fine. All right. Fine. Okay, cool.
Something I was thinking, because I'm also just going through the standard compiler material like undergraduate, is I really like Brill as an idealized LLVM, but the Brill is like the teaching IR for one of Cornell's courses. But I wish there would be like something I'm hoping to do with Brill is see that like with the register allocator, see like how everything that is talked about here, the tribal knowledge of like all the heuristics, how to balance the inlining with the register allocation, trying to get that into like the learning experience for myself for Brill.
A major goal for C2 was that more inlining did not blow the allocator out and have it go crazy. as that was the major fault. I was fighting with all all allocators prior to C2, and that meant that inlining was always very fragile. You inline some, you got faster. You inline more, you got faster. You inline more, the allocator went crazy, spilled like hell, and you went slower. And it was very hard to get that knee in the curve without getting close to the edge of the knee without falling over. And so a major design goal for C2 was that when you over inline, you have too many things live, the allocator didn't do any worse than call or callee save overheads would otherwise do.
How large of a data set do you think is minimum to reproduce in like a sort of
Your corpus?
like that yeah, corpus to reproduce that knee in the curve? Because
Um,
Brill, the Cornell like Brill idealized LVM does have test programs, so I was hoping to get to that where I can actually reproduce for
you
myself.
want you want somebody's fairly large corpus, like at least 100 like full programs, and they have to be some way to validate the quality of the allocation. A way is to say runtime speed. A way is to do things like count, but then you have to have frequency scale. So you have to have some way that you've thrown into the program or the allocator got frequencies with maybe static heuristics based on loop depth, whatever they are, and emit that and pull it out and say the allocator thought he did this quality of spilling. And then you can go through and do your own and have a metric you can do a comparison. For simple, I have the loop nesting depth and I have spills and I scale them, spills by loop nesting depth, and I get a metric on how well I allocated this program, which I use for, the set of things I have in simple. I have 10 or 20 reasonably allocatable things. It's, useful to look at. For C2, it was Java. So I quickly went to, 1,000 functions, 10,000 method programs, and had larger counts.
Do you, Yasser, do you see that with your compiler, I guess, backend? Do you have enough of a corpus to see like that knee in a curve?
Um, I have enough to see it, but like only because I can artificially cause it.
With like fuzzing?
Yeah, basically, or like just like forcing basically everything to inline. I've got a
I
current
want to
test
give
that
Simon
just
a chance, Ryan. Sorry.
What's it?
Simon, are you interested in talking about, because you've been working on stuff and you hit kind of a nice, you crossed a nice threshold this week. Did you want to present? This will be completely unrelated to registrar allocation.
Yeah, probably, but I didn't want to interrupt you guys. I thought that was pretty interesting.
Well, Ryan's
So,
trying to pivot to ranges and iterators, which is a good topic, except we're just going to run out of time. And we could keep pounding on registrar allocators if you want, because the last question was really good. How big a corpus is big enough? I would like to say 100 functions, not 100 functions, 100 programs. So call that 1,000 to 10,000 functions, but you need to get a metric that you can scrape out. If you have 100 programs that have runtimes that are expected and you can execute them and do compile and program speed, that's best. Second best might be I scrape the IR for frequency data and I use that to get a spill code estimate. You're doing your own allocator, you can print it yourself. That's what I do with simple.
I thought this was really funny. I will keep their names out of it, but I asked a compiler dev, why is the compiler you're working on slower than another compiler? Because I tried it on all my programs, and the other one is always faster. And his answer was, we care about having bad code run better than having the fastest code. I don't know if that's valid, because I think it's
valid.
just
No.
because if you care about that, wouldn't you
No.
just like fix it?
That's entirely valid. This is one of the
that's the whole premise of debug builds, basically.
It's a major thesis for C2. Your crappy Java code does okay.
Because
And I tried hard that if you write really tight code that looks like high performance C code, it executes like high performance C code. But if you just write generic junk Java code and it's bad code, you still do okay.
Because his code was 5% slower. And I know you can change one line and get a 10% overall program speed increase. So I thought, like, why do you care? If they don't care about optimizing their program,
Not at
Like,
5% mark. No, time to market. I got my WYSIWYG startup program hit the market ahead of by competition by a month, and people bought mine instead of yours, and then I get the minimum quorum necessary, and I'm Facebook now, and I'm a billionaire. I won because I got there first, and I
no, no,
got
I
there first
mean,
because I didn't care about the low level performance details.
no, I mean like my code ran 5% slower on that compiler,
Hmm.
and like I just didn't understand if you can just change a line and get like you know
Yeah,
thousands of seconds of increase just by changing one line, then why do you care about making this
programmer
so
writes a
great?
better algorithm, wins every time over whatever a compiler can do. Hmm.
Yeah, yeah. So like why would you want to focus on making bad code faster if you could just
Because it means the market as a whole values it's the same reason that while we were in the era of PCs going faster every and what's the say Simon's got stuff. While we're in the era of chips getting faster every generation, you just didn't care. You waited and you went and bought the next faster one from Intel. And Intel said, next year's chip is 50% faster. You just bought it without question. You didn't bother to test, you didn't time it, you didn't profile it, you didn't care. You threw your money in Intel and you took the chip and you walked away.
I just figured they wouldn't care that it's a little bit faster. I
No,
care
but
because I want
most
the
people
fastest.
just took the math. So if I said this year's compiler will make your code 5% faster, and next year's another five, and next year's another five, how long until you upgrade? You go to the JVM. Yeah, your Java 5, your Java 8, your Java 17, Java 21, Java 24. If each one is like 5% faster, you're going to question the upgrade? No, you're just going to take it. Oh, I had to fiddle a few things because there are slight incompatibilities. It's guaranteed faster, and the next one's faster yet. Okay, I take it. There's a thing there that says it's just better without any effort on my part. I'll just take it.
Okay, yeah, I just chose the compiler that compiled my code faster,
Yeah,
but
that's fine. And there's a flip side is the common failure mode if you don't have this mentality of junk code goes well, is that some junk code sucks really bad on your system because you didn't handle that case. And then you have these potholes. And for the consumer of this thing, is my code going to land in a pothole and suck or not? I don't know. Do I want to find out? Maybe I'll just go to this guy who says there are no potholes. My roads aren't great, but they have no potholes.
okay, I can buy that. Yeah.
Okay.
Performance cliff.
I'm sorry. Yes.
That's the
You
term
didn't fall
in
off a
JavaScript land.
cliff. Right. I have this funny, very similar scenario. I would love to have no potholes on my mountain roads. The I would take a bad road with no potholes over a nice fat big road that has a bajillion potholes. When Highway 17 gets a pothole, by God, Caltrans is out there right away, filling the holes on Highway 17. Oh God, you can't have holes there. Yeah, yeah, making crap code do well, 5% better versus making HPC code go 2x faster because I'm computing weather tomorrow. If your target's the weatherman, you want one thing, and if your target's everybody in Silicon Valley, you want the other. Fine.
There's also like for the like there's a what am I trying to say? There's also an analog to like at the cloud infrastructure level in general, just infrastructure
Yeah.
Levo. Because I was working on infrastructure at a company. We had like 10,000 engineers, and a lot of those engineers are not like compiler engineers, infrastructure engineers. They're like application product engineers that don't
Right.
want to touch any infrastructure, whether it's like microcode assembly or whether it's like
Right.
infrastructure as code, Terraform. And so it's like when you're discussing with an inference, like how can we make it so they don't have to touch a thing because they don't want to. They want to write their Java code, their Go code, their
Right.
Python, their JavaScript. They don't want to discuss what we're talking about.
Right. And then some guy's paying the bill in the cloud, and the bill went 5% smaller because the next rev of the compiler was 5% better. It did dollars on the bottom line, and you have a huge stack of engineers doing good shit, but they're not compiler specialists, and they probably shouldn't be. So yeah, absolutely. Okay, wait,
Well,
I'm going to pivot and say, Simon, you got 15, 20 minutes.
All right. Do you want to share your Google
Absolutely. Just a
Docs?
second.
I wrote
I
pages,
will
but
hit the
I
share
think
button.
I can give you the cliff notes pretty
Okay, I hit the
fast.
share button. You're welcome to share.
No, you just share your Google
Oh,
Docs.
what am I sharing?
The Google Docs you.
The Google Docs. Oh, I'm sorry.
Yeah,
Yeah, okay. Now I'm all confused, so I gotta find myself again. All right, done. And then you have something in here. So at the bottom or the top?
Yes,
Oh, at the bottom.
yes.
Here we
Scroll
go.
down.
Update on core.
So yeah, I had two big things that I worked on recently. One was my general drive for more keyword consistency, especially like getting all keywords of the same group lined up. So I got rid of import because like there are plans for export and for module. So all the namespacing is 6 letters. And I changed a few things to contextual keywords for and in. And that was as expected. It's less painful for in because for is like this important keyword that it starts introducing things, while in basically only follows if you had a for before. But it's manageable because I want to get rid of for anyway and only have while and stream
Oh,
combinators.
you only have while. I like for loops myself. But fine. I
And
like them for fixed iteration lengths. As it's a hint.
yeah, I
know
hope
that.
I can replace all of that with stream combinators,
Oh, I
flat
see.
map filter stuff. So let's see how that works. And the other thing is that I really, really want to get rid of impl, which is like the second topic down there.
This is
If
the
you
picture.
scroll down.
Oh, scroll down here. Yes. Ooh,
Yeah, exactly.
stuff
So
uh,
I have inherited this impl design from Rust, which resembles it pretty closely, except that instead of uh, the XML brackets, the less than greater than symbols, we use the brackets for generics. But apart from that, it's comparable.
I hate
And
brackets for generics, but yeah. Oh, you
and
don't have them.
I have the brackets, not the less than greater than.
Yes, the less than greater than. Yes, the brackets are fine. Fine.
And so basically, I had a look at what impl is actually doing, and I figured out that basically all the things impl does are 3 separate things, which is always good to know that a keyword is not even isn't even like one use case, but 3. And you can roughly sort the use of impl into these definitions that basically just add methods to existing types, which is like number 1. And I showed this in the first screenshot. So before you had this syntax where you had like class and you only mentioned fields there, and below that you have an impl for that class, and that actually adds the methods. And in this case, it was like a huge workaround that made everything complicated for not having a class with a constructor and some initializers. So that use case, that number 1, I'm in the process of replacing that, and that looks pretty good so far.
Mm-hmm.
Number 2 is basically impl definitions for implementing a trait. And that's also one of the things that irritated me about Rust and also in that language, that basically what comes after the impl keyword is either the trait name or the type name, depending on whether there is a for behind it. So if you have like impl list, then the list, that's the type. If you have impl hash for list, then the thing after impl, the hash, is the trait, not the type. And that really, really annoyed me. And I found a good solution to that of basically saying, well, I have a trait, I want to implement a trait, I just say trait name for type name.
Right.
And I'm pretty happy with that, and I think it's you could argue it's pretty similar to like class string versus class string implements char sequence or something. You have
Yeah.
like
Right.
always the trait, always the class, always have like the type, and then you say, well, there's another thing that's implemented. And I also replaced that stuff, and it's also looking quite good. And the biggest problem I'm facing so far is number 3, which is when you scroll down the last screenshot. Exactly, it's basically extension methods. So basically number 1 was class bodies methods. Basically number 2 was interface implementations, and number 3 is extension methods. And you see there, you basically don't have a type, but you have like some kind of special, more complicated thing, this impl option of t, which basically says I have an implementation of my method flatten, but only if my instance is of type option of t.
Mm.
And that's of course not fitting really well into either category of those before, because it's not a body that could go into it's not a method that could go into the body of a type, and it's also not implementing a trait. So one thought I currently have with this number 3 is that I'm saying, yeah, well, I could define a trait with that exact signature and then basically implement it, which has the advantage that it also solves the question how to bring these extension methods into scope. So if someone defines such an extension method, you can basically say the method is only in the scope if you implement its trait. And that way you could have multiple people extending a type with the same name, and as long as you don't import both, it won't clash, and it's always unambiguous. But I am still thinking about it. I still hope there is a more intuitive replacement for that. And I think
So
that's
the
it.
Just quickly,
so
sorry.
the
I think with your option example, it's probably a bad example because that should be a trait. Like options are monads, so you've got the trait monad. It's already there. It's already well defined.
Yeah, I was actually
You
super confused with this coming from Haskell, because in Haskell that would be maybe and the flatten would be fmap. At the moment you says that an option of a type has an fmap, then you're done. And then you should never be even able to say that an option of an option has something else. So the very possibility of writing this to me is very confusing and kind of feels wrong. I would encourage you to use some simpler example, maybe option of
Mm,
comparable or equality comparable of option. Just don't
yeah.
repeat the option because this is extremely confusing.
I mean, I have maybe a better example with I think contains. Basically just the method contains, and it has basically a constraint that the t of the thing I'm comparing should be equals. And yeah, maybe that's a better example. But yeah, currently I'm a bit limited uh, in the monad department, because I don't have higher kinded types, so I can't express the trait in its full
Yeah, but
generality.
even without this, I mean, this would be just a functor. So in Haskell, functor is something that just has an fmap, and presumably
Yeah,
this
but
fmap has to obey factorial laws. And I guess you are coming from Scala, given that you use word flatten. So in Scala, it would also be enough to just say that you can flatten an option of something. And then you just don't specialize what that something is. So you should never be even able to use option of an option of the, because option already should have an flatten.
Yeah, that's true. It's just I mean Scala also has higher kind of types, and I think you also need them for functor. So I
Maybe
think
some
it
simple example like equality comparable or orderable when you can have less than or equal, like Haskell's EQ or Haskell's ORD. And you mix that one with option. That could be simpler.
What the extension
Regarding
methods really
the
allow you to do is do the ad hoc stuff that you're just doing specifically for one program. And it's not part of some kind of wider arching pattern or method that you're using. So if you've got type conversions are really useful. If you've got some domain specific type conversion, you can put it just on that type or that set of types that you want to do the conversion with. Sending stuff across the wire, deserialization, things that you're calling your very own specific code. Those extension methods do make taking the verb and putting the verb after the noun is the English way of speaking, which makes it much easier.
I was thinking regarding the third case that implementing this as a trait with a method with a default implementation, if it's possible for someone to come in and overload or redefine that as it would be in Rust, that would seem kind of wrong, I guess. Like you have your option of a T, or maybe it's an option of a part of a comparable, and then someone comes in, they say, yeah, I implement this option comparable trait, but actually I'm gonna implement it with a different function. That would be really surprising. So in that sense, I don't see the trait being the right option there.
I think that's just another bad example. It's my opinion that comparable and equality shouldn't be on the object. It's a subjective decision as to whether or not two things are equal. And if you put it on the object, yeah, you end up in that scenario where the default doesn't work for me. How do I override it? Oh, I can't, because the language is now I've got to copy the entire hash map declaration because it annoys me.
I think Ecstasy, Cameron's project, he has two versions of things. One is there is a default for convenience, and there's a hash map that takes a hashable, so you immediately get to have a separate hash function for a different class of things. So one of the shows up in compiler land is I want to say two things are global value numbering equals, which has a default hashing and equals function. But sometimes I want to have a different hashing function for unrelated things to do with nodes. And so I want to have two different hashing and two different comparable for the same node object, depending on context.
Oh yeah, the hash map was just a one symptom of it. Look at JavaScript. You've got equals, 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 dot equals, like because every single time they're always
yes, more equals.
Yeah, how like there's so many ways of comparing things, and it's all subjective.
Equals than others.
Yeah, it's a design flaw because fundamentally you need somewhere between 0 and 433 different equals for the same thing, right?
Yeah.
And so you don't want, and Simon can attest to this, you don't want the 433 equal sign operator, because that exceeds the column width. But if you don't design for it, you just keep adding equals to the operator until you look as ugly as JavaScript. So
yes,
I think,
but it's fine. We're getting 8K monitors soon, so column width isn't a problem. You just measure it with the you tape measure and you know what equals you're calling.
So I think there is a case to be made for being able to separate the concept of equality from the structure that is being compared for equality. So in Java, for example, we created years ago, when we ran into this repeatedly, we created an interface that represented, something that had an opinion on equals and maybe hash code and maybe ordering as well. So, so you could separate those things from the class of objects themselves.
But
Yep.
And of course, for the general case,
I kind of want to circle back to what Simon was actually showing, which is effectively globally defined helper methods or automatic derivatives of these possibly self-defined equality methods, like there is now the added example replacement, or the identity function for option T. Identity function definition is there given if self in some actual, then actual is identical to val, else if none, then false. So you're given two things that can compare identity with each other, but one of them is in an option, and now the language defines, in a way, the standard library defines, hey, you can compare an option of a T with T, and I will automatically derive this for you. But if you take that into an interface, if you turn that into an interface that can be defined individually on each type, now you get into a situation where, yes, usually some T will equal T, but somebody made an overload where actually they mean that none equals T, because, it can be overloaded now. So this isn't about whether or not equality can be overloaded. It is whether or not some kind of a effectively modular wrapper, or some kind of a wrapper over a user-defined T, if it compares reasonably equal or consistently equal. And there, maybe I'm rambling a bit, but my opinion at least is that yes, you should be allowed to define equality, but you shouldn't be allowed to define option T equals T equality anymore.
But wait, surely you want more rope to hang yourself. I don't know. Somebody wants
True. That is definitely more rope.
Yeah, somebody wants it, I'm sure. And who am I to say you can't have the rope to hang yourself?
At least with the trade approach, we're not running into coherence issues from what I'm seeing, because we're basically not relying or expecting that there is only like one instance of the type class in existence, but expect only one to be in scope, and that's a method, or that's a function that's being called.
All right. I'm going to wrap this up shortly.
Yeah.
Got any more things going on here?
For someone interested in eventually going to GPU compilation, I have my weekly question for Cliff, which is like how's Mojo and MLIR?
Oh dear. I am not fond of MLIR. Mojo is an early cut language. It has some, it's too young, learning curve things going on with it. Not learning curve. What do you even call it? Immature problems, just due to the where it's at in the life cycle of a language. That said, I am still sorting my head out at modular about where I can make a better impact. It's not clear to me that a deep dive into MLIR is my best effort. It might be, but it's not clear that that's what it's going to be. And then I'm taking my 2 weeks at Burning Man to basically ponder that question. Yeah. I probably won't get into LLVM deeply because modular mostly does their thing and then at the very last second hands it off to LLVM for cogen on, especially on the GPUs, so that the hardware vendors can spin out a new LLVM for their particular GPU, and modular doesn't have to care. Is plug and play the back end and walk away from it. That's sort of where I'm at with that one right now. And I get my
What are
2 weeks to
those?
go sort myself out.
What are those immaturity problems, like ecosystem
Yeah,
wise, or
basic implementation stuff. Like the debugging story is kind of, it looks good until it crashes hard. The language server routinely crashes hard. And then it restarts itself and crashes again a second later and stuff. So you don't necessarily get the things you expect out of a language server because it's just falling over constantly. That being said, these are all things that they're very well aware of, and work is being done on them, and I'm sure they're improving. I don't know, I can't say what the time frame would they become more stable, but it's clearly well understood and being worked on. Now, do I want to pile in directly on, the better debugging effort or language server or whatever pieces, or do I want to work on, there's a bunch of features they want to add. They have hacked in features to make it work for GPUs and particular ones of various kinds that don't compose nicely. And they know that and they want to fix that. And now do I pile in there? A lot of things to be done. There's a huge pile of to-dos and things to go forward with. So
yeah,
I'm
I'm
not
very
ready to
interested.
I'm not ready to write a large, complicated, non-GPU targeted program in Mojo. Somebody could, but I'm not quite ready to go there. If I was to go target a GPU, yeah, definitely, but that's not where I'm at.
It'll be interesting to see Modular's roadmap because they have planned to open source the compiler like next year, right? So
I'm not going to say what the time frame is. You have to go look at the public announcements on those. I
yeah,
have
I think
internal,
that's what it is, like next year or something to
right,
open source
right,
the compiler
right.
target.
Yeah,
So
I have internal knowledge that I can't bring up, so I'm just going to point you, say, go read the external docs, and that's where that is. Okay. I'm going to call it because I have many things to do because I am packing for a 2 weeks camping trip, more or less. And that means that I'm not here the 22nd, the 29th, and should be back September 5th.
All right.
And
See you all.
this was a very fun go round, and happy to see you again, Levo, and you're totally welcome back on the Discord. If you don't automatically get in, if you want to get in,
I
you
don't have any
do it.
social media
I'm
except
sorry?
for I have no social media except for Reddit, and that's only because
We
I post
are
weekly
I'm
devlog.
just saying, reach me if you need to reach
mm,
me before
Okay.
Sunday.
we are not that social, Evo. No worries.
Yeah.
All right. Um, it was very fun. Nice seeing everybody again.
All right.
Until, 2 weeks from now, 3 weeks from now.
All right. See y'all.
Bye bye.
Goodbye.